All right, good morning. This is a short presentation about Noether's theorem in quantum field theory, and we'll just get right into it with a motivation. We can consider the Lagrangian of a complex scalar, which has a simple kinetic term and a mass term. And you can notice that this Lagrangian is invariant under a global change of phase where phi goes to an exponential of minus I alpha times phi, where alpha is a real number. And this is an example of a continuous symmetry of the theory. Now we will see that continuous symmetries lead to classically conserved quantities. One may already note that such a symmetry of the Lagrangian does not necessarily imply a symmetry of the path integral, since there's always the integration measure to worry about. But let's get into that statement a bit more, because if we say that there's a symmetry of the Lagrangian, well, we can vary the Lagrangian with such a symmetry parameter alpha, and then we can just write that out as taking derivatives of the Lagrangian with respect to the fields and the change of the fields with respect to the symmetry parameter. Now, to go from this line to the next, we merely insert one term like this and subtract it also. And note also that there is a sum over the field ndxn, because I'm just going to say that there may be many fields phi. Note also that we specialize to global symmetries, where the variance of fields with the symmetry parameter is 0. Now, if that's not the case, you can always compensate for that with the product rule by just subtracting a term for that. One immediately recognizes in the first term that this is just the Euler-Lagrange equation. Therefore, if we're on shell, namely if the classical equations of motions are obeyed, we see that this variance, or rather this derivative, vanishes. And therefore the term within brackets defines a current J, which we'll call J mu, and that's the Noether current. Now we'll go to an example. Consider again the Lagrangian that we had of the complex scalar that had an aforementioned global phase symmetry. Well, infinitesimally then, we can write the variance of the fields, the change of the symmetry of the fields in the following way, where there's a linear term in alpha, and therefore the variance of the fields become the following things. And then to find the associated Noether current to this symmetry, we just plug these into the equation we found just now. The computation has by this point become very straightforward. We sum over two terms because we have the phi and a phi dagger field. You know that this parameter is proportional to phi, that's this term, and that the variance of the Lagrangian with the derivative of phi is just the derivative of phi dagger, and the same for the other term. Now, why is this useful? Well, first of all, the current J is conserved, but with the Noether current J, we can define a quantity which we'll call Q that's conserved, and that's just defined as being the spatial integral over the 0th component. This is conserved if we assume that the spatial component of the J's vanishes at infinity. Why is that? Well, let's just calculate the time derivative. We put that into the integral, and we use the equations of motion, namely the conservation of J, to write this as a divergence, which, if we assume J falls off infinity, vanishes. This is also what you're used to in just classical electromagnetism. Now, in summary, global continuous symmetries of the Lagrangian imply the existence of the Noether current, which is defined in the following way. This Noether current has the following equation of motion, which is just the statement that it's conserved. And a conserved current gives rise to a Noether charge, which is defined as the spatial integral over the 0th component. I thank you for your attention.